This week's lab will make use of the Gran plot titration method. This is a very clever method to determine the equivalence point in an acid-base titration. We'll be following the titration with a pH meter, measuring pH after each volume of addition of titrant. And this method is useful because it's going to use data before the equivalence point. So normally if you're following a pH titration, an acid-base titration with a pH meter, you need to be very careful to get good data right around the equivalence point. And that's hard to do because around the equivalence point, because the solution isn't buffered very well, the electrode tends to be really sluggish, and so you have to wait a really long time, taking data points really close together, waiting for that pH electrode to stabilize. This method avoids that by using data before the equivalence point. So to talk about how this method works, we're first going to need to discuss a couple of other important effects. These will dovetail nicely with the content in Chapter 8 of Quantitative Chemical Analysis by Dan Harris, the 9th edition. So we'll be talking about that in Chapter 8. So we're going to talk a little bit about ionic strength effects. So let's consider this reaction between the aqueous iron 3+ ion and the thiocyanate polyatomic ion. So iron 3+ is kind of a pale yellow color in solution. You might get that from taking iron 3 chloride and dissolving it in water. And thiocyanate gives us a colorless solution. Again, you might get thiocyanate by dissolving some sodium thiocyanate in water. So these two ions can react together to form a complex ion, this iron thiocyanate complex that's here on the product side, and it's red colored in aqueous solution. The picture to the right shows in a panel A, two beakers, the same solution there, just divided into two beakers at equilibrium. And so we see that the red color kind of dominates visually. So this is a formation reaction, and if we were to go in and write the formation constant, the equilibrium constant expression for this reaction, it would look like this: normal procedure, products over reactants. So given the red color of these solutions, we might guess that the product sort of dominates the formation of this reaction, and so we would tend to favor the products. Could be that it's just a really strong absorber. We don't really know that, but maybe it favors the product. So what's interesting is down here in the lower panel, what we're going to do to the right-hand side beaker is we're going to go in and we're going to add some potassium nitrate to that solution. So just some potassium nitrate solid, just a little bit. So that's going to give us a source of potassium and nitrate ions in this solution. So it turns out that those potassium and nitrate ions aren't involved in this reaction really at all. They don't react in any important way with any of the components of this reaction. They are truly spectator ions. They just sort of hang out in solution. But interestingly, you'll notice that when we add those ions to this right-hand side beaker, that it appears as though the reaction shifts back to the reactant side. So we make some more of that pale yellow iron product. It's as if adding the potassium and the nitrate has broken up our complex ion here and formed these ions. And in fact, if we were to do a little experiment and graph our results, so on this axis, we're just going to plot this ratio of products concentrations to reactant concentrations. So maybe there's a way that we can measure what these concentrations are. And down here, we're just going to plot the concentration of the potassium nitrate that we add. So this will be in units of molarity, let's say. This will be our equilibrium constant expression effectively, and so it will be unitless, but it does have a numerical value, and it starts up here maybe at around 300 under these conditions, and we're going to cut it off here at the bottom at about a value of 100. And what you'll see is that if we start with 0 moles per liter of potassium nitrate, we get a value for this ratio that's pretty close to 300. And then it starts steadily decreasing, and it kind of levels out around 100 when we get down here to about 0.7 molar or so for the potassium nitrate concentration. So this is interesting, right? This ratio here is supposed to be constant, but it appears that it is changing. Yet based on everything that we know about Le Chatelier's principle, we're not doing anything to this equilibrium that it can adjust for. So there are no common ions present, we're not changing concentrations, we're not appreciably changing the volume by adding a sprinkling of this salt, we're not changing the pressure, we're not changing the temperature. So what's going on here? Well, it turns out that these ions are affecting this equilibrium in an important way. And so we need to explain what's going on. So I'm going to scroll down, give us a little bit more room. And so let's think about what ions we have in solution. And so we're going to imagine, just for sake of argument, that we're going to pick an isolated iron 3 ion. So here it is. I'm going to represent it as a little sphere. It's floating around in solution. And somewhere else, some distance away, there might be a thiocyanate anion here. All right, so those are supposed to be spheres, but you get the idea. So what we're going to do is imagine that we're going to take a little chunk of solution around this iron ion and the same size chunk of solution, again, a little spherical shell around this solution, around this ion right here. And we're going to think about what's inside this little sphere, well, besides the iron ion. Well, of course, this is dissolved in water, so there are going to be lots of water molecules, so I'm not going to draw those in. Same thing's going on over here. So we also know we have some other ions that are present. I'm going to make a little table here. We've got iron 3+, we've got potassium, and we've got this iron thiocyanate complex. Those are our positively charged cations, and for the anions, we've got nitrate and thiocyanate. There would also probably be the counter ions that we got these salts from in the first place. So I had mentioned chloride earlier, so there might be some chloride in here. There might be some sodium. And then, of course, from the autoprotolysis of water, water will react with itself as an acid base a little bit to give us some hydronium and some hydroxides. But there's very, very little of that in there. But anyway, we've got these ions also floating around in solution. And so there's a chance that in this big little circle of solution that I have here, that there will be some ions that will have drifted in here. So I'm just going to draw, without thinking about which ones they are, some little plus and minus signs here so that we can think about those ions. Now it turns out because this iron has a +3 charge, right? These negative charges are a little bit happier to be around this +3 charge than are the positives. So even though these ions are constantly diffusing into and out of this spherical shell, on average, over time, there will be a few more negatively charged ions than positively charged ions. And so inside this little sphere, we create an ionic atmosphere that has a little bit of negative charge. I'm going to use this lowercase Greek letter delta to represent a little change. And it's negative. So there's a little bit of negative, what we call an ionic atmosphere in here. The same thing is happening to our thiocyanate, right? So we've got positive charges and negative charges that are diffusing into this spherical shell. But on average, there are a few more positive charges than there are negative charges. So inside here, we're going to have a net partially positive ionic atmosphere. Now, because the positively charged iron 3+ is attracted to the negatively charged thiocyanate, there will be a force of attraction between them, right? And when they get close, they would actually form this coordinate covalent bond leading to the coordination complex. So there's a force of attraction between these guys. But if we consider their ionic atmospheres, then in this case, we would see that over time, on average, what is the total charge inside this sphere? Well, if we just had water and the iron, the total charge would be equal to +3. But because there are these negatively charged and positively charged ions in here, this total charge is going to be something that's a little bit less than +3, because on average we have a few more of these negative charges than we have the positive charges. Same thing's going on over here. The total charge inside this sphere of solution that we're looking at is going to be something less than -1. So because of these ionic charges then, this force of attraction is going to get diminished. So I'm going to indicate that just by erasing some bits of the line here and making it more of a dotted line. So what's happened is the force has decreased. So the force of attraction between these guys So the force is decreased due to the ionic atmosphere. An analogy that I sometimes like to think of, imagine that your favorite pop star was in town and you really wanted to go see your favorite pop star. But when you went to wherever they were located, you discovered that they were surrounded by paparazzi with their big camera crews and news media, and so really you couldn't get in to see your favorite pop star very easily because they were sort of screened out by all these intervening paparazzi. Well, in this example, the pop star is kind of like the ion, and you're sort of out here, the anion. You're attracted to the pop star over here, the iron, but you can't really get to see your pop star because of all the intervening ions. They sort of screen out your attraction towards that pop star. And we would imagine the more ions there are, the more screening there is. And that, in fact, is the case. And so what happens is that the ions that are in solution, and so what we can conclude is that ions in solution are going to stabilize other ions in solution. In other words, it's going to be harder for these ions to recombine because they don't feel as much attraction for each other, and there are these other intervening ions in the way in their ionic atmosphere. And we can see that in our reaction up here, that these two ions, iron and thiocyanate, are less likely to come together as the ionic strength of this solution increases. And so we stabilize these individual Fe3+ and SeCN- minuses in solution, so they are less likely to combine. And that's why our solution turns yellow, even though we're adding a salt that doesn't react with any of the components in our solution. So that's the ionic strength effect. And so we're going to be interested in measuring, so what is the total charge in our solution? What is the total charge due to ions in our solution? And we call that ionic strength. And so ionic strength measures this property. It tells us something about the total concentration of charge in our solution. And ionic strength is defined this way. So we give it the symbol mu, that's the Greek letter mu, and it equals 1/2 C1 times Z1 squared plus C2 Z2 squared, and then we would just keep on following that pattern. And what are the C1s and the C2s? Well, each CI, that's just the concentration, and typically we will represent that in units of molarity of some particular ion, I. So we're just going to label each of the ions with this little I index. So I might be a sodium cation or an iron 3+ or a thiocyanate, SeCN-. So whatever. And we just add all these up for all of the ions that are in my solution. Z sub I is the charge on that ion. So it might be +1 for a sodium cation, or +3 for our iron ion up here, or -1 for the thiocyanate. So whatever the charge is. And we're going to be squaring that charge, so that will get rid of the pluses and minus signs for us. So let's just do a quick example of using this equation to calculate the ionic strength in a solution. So in this example, let's imagine that we have a 0.010 molar sodium sulfate solution. Okay, so we know that sodium sulfate, when you dissolve it in water, it's a soluble ionic compound because all group 1 metals are soluble ionic compounds. And so we predict it's going to completely dissociate into ions to give us 2 moles of sodium cations and 1 mole of sulfate. So we want to calculate each of these things. So we need to know what is the concentration of the sodium and what is its charge. The charge is easy, right? So it's just +1. And so we need to figure these things out. And then we'll do the same thing for the sulfate. So let's go ahead and calculate those concentrations. So in square brackets here, remember that means molarity. So the molarity of our sodium, how do we figure that out? So we start out with a solution that's 0.010 molar, and so that means moles of sodium sulfate, Na2SO4, per every 1 liter of solution. And then we see from the stoichiometry of the reaction that we produce 2 moles of sodium cations for every 1 mole of the whole compound, Na2SO4. And so that means we're going to have a concentration of 0.020 molar in sodium. For the sulfate, We can use the same reasoning, but we see that we have one-to-one stoichiometry, so that makes it easier. Our our sulfate concentration is just 0.010 molar, because it would be 1 mole of sulfate for every 1 mole of sodium sulfate. All right, so now we know two of those concentrations. Let's substitute that into our ionic strength equation. So mu is equal to 1/2 times the concentration of our first ion. Let's let that be the sodium. So that's 0.020 molar. And then we're going to multiply that by the charge, which is +1. That gets squared. Then we add that to our other ion that is in solution. That's sulfate. Its concentration is 0.01 molar. And we're going to multiply it by the charge, which is -2. And that gets squared. So multiplying things inside the parentheses here, we've got 0.02 times 1 squared, which is just 1, so we've got 0.02 molar, plus -2 squared is +4. +4 times 0.01 is 0.04. So we add 0.04 and 0.02 molar, we get 0.06 molar, and we take half of that. That gives us our ionic strength of 0.030 molar. So ionic strength is just a metric that we can use to talk about the total concentration of ionic charge in our solution. So even though this is a 0.01 molar sodium sulfate, because we get 3 moles of ions and the sulfate has 2 units of negative charge, so that negatively charged ions count more when we're doing ionic calculating the ionic strength, we have a total ionic strength of 0.030 molar. All right, so we're going to be using ionic strength then when we think about how to fix this problem with this fact that our equilibrium constant appears to no longer be constant, right? So it's not constant because of this ionic atmosphere effect. And so we need to include that effect in our sort of theory for equilibrium constants. All right, so we're going to think about how to incorporate ionic atmospheres into our equilibrium constant. And so what we're going to define is a new term called activity. And this will be a little bit confusing at first, but hopefully it'll make a little more sense after we kind of apply it. But basically, it's an effective concentration for solutes in solution. So we're going to replace all those square brackets with this thing called an activity. And the activity corrects for these ionic strength effects. And so let's think about a general equilibrium reaction. So we've got A moles of species A reacting with B moles of species B, and that's in equilibrium with our products C moles of species C plus D moles of species D. Again, the capital letters represent different chemicals, and the lowercase letters are just the stoichiometric coefficients that we need to balance this reaction. And so what we're going to do is write a new activity-based equilibrium constant. And so everywhere we would before write concentrations, now we're going to write activities. And so we're going to represent activity by this kind of curly A here. And so products over reactants, we still have the activity of species C raised to the little c power times the activity of species D raised to the little d power. Products over reactants, so we do the same thing with our reactants, the activity of species A raised to the little a power times the activity of species B raised to the little b power. So what is this activity? Well, the activity, let's say, of species C is defined this way. So it's the molarity of species C, just like we saw before, and we're still going to remember that we divide by the standard state concentration, which would be 1 molar for solutes. And then what we're going to do is we're going to multiply this by a coefficient. So this little thing that looks like a fish swimming downwards that I just drew is the lowercase Greek letter gamma, and it gets a little subscript C so that we know that it's associated with chemical C, species C. And this thing right here is called the activity coefficient. And so the curly A here, again, that's what we're calling the activity. All right, so basically what we're doing is just we're going to take our usual expression for equilibrium constants, and we're going to replace anything with a square bracket of substance X. We're going to replace that with an activity. And an activity is going to be the concentration times an activity coefficient. And so it's these activity coefficients that are going to include or correct for these ionic atmosphere effects. And these coefficients, they will depend on the different chemical species. So the activity coefficient for iron 3+ will be different than the activity coefficient of thiocyanate, and they will also depend on the ionic strength of our solution. And it also turns out temperature, but we already know that equilibrium constants depend on temperature, but our activity coefficients will also depend on temperature. So I'll just kind of make a side note about that, and T for temperature. So as you change what the chemical identity is, as you change the ionic strength, as you change the temperature, these activity coefficients are going to change their numerical values. So there are some ways that we can begin to understand these activity coefficients. So there is an extended Debye-Huckel equation, and this is a theory that was used to calculate what these gammas are. And you should ask your favorite physical chemistry professor if you would like to know the physics behind how this equation was derived, but we're just going to write it down. So it's written down this way: the log of the activity coefficient is equal to negative 0.51 times z squared times the square root of mu divided by 1 plus, then we have a fraction that adds to that 1. There's an alpha here, that's an alpha, Greek letter alpha, times again the square root of mu divided by 305. So this is an odd equation with weird numbers in it, like negative 0.51 and 305. But let me tell you what all these things are. Again, Z is the charge on the ion. Mu is the ionic strength. I guess I should tell you that this is the charge on the ion, that it's what we call a relative charge. So it's relative to the charge on a single electron. So iron 3+ would have a relative charge of +3. A sodium cation would have a relative charge of +1, that kind of thing. So it's the charges that we're used to seeing. Ionic strength, we've already talked about that. That's going to be in units of molarity in this case. And then this parameter, alpha, is really just a fitting parameter, but it's associated with the hydrated ionic radius. So what is that? Well, that's the radius of the ion, so like our iron 3+. So how big around is that guy? But then we're going to include all of the water molecules that would attach themselves and float around with this iron molecule. And so they're going to make a sphere that has a certain radius, and that's what alpha is. And we're going to measure that in units of picometers. So where did all these weird numbers come from? Well, they came from physical constants transferred into units that make the units all cancel out, because activities like things that we put into equilibrium constant expressions are unitless. Activity coefficients are also unitless numbers. Right, so how is this activity a unitless quantity? Remember, when we take the concentration and we divide by the standard state, it becomes unitless. And then activity coefficients are unitless, so activities are going to be unitless. And so when we put in the right units and everything, this is the equation that we get out. So we're not going to use this equation, but it tells us a couple of important things. So here's some observations. First, we can see that as the ionic strength increases, in general, the activity coefficient will decrease. So these get to be smaller. We also notice that as ionic strength goes to 0, so we don't have any ions present, that the activity coefficient will approach 1. So they become equal to 1, in which case all of our activities become identical to just plain old concentrations. So that's one observation. So as we increase the ionic strength, these ionic atmosphere effects become more important, that our gammas get smaller, okay? And then as we make our ionic strengths close to 0, our gammas go to 1. The other thing that we notice is that as the charge on the ion increases, we will see that these gammas get sort of larger in magnitude. So we're going to see greater activity effects. And so these really become important when you've got charges that are greater than or equal to, say, plus or minus 2. So anything that's polyvalent, so more than a +1 or -1 charge, then we start seeing even more important activity effects. So these are due to those ionic strength effects. And number 3, the smaller the ion, and we're thinking about the hydrated radius, so the ion plus its water molecules. So the smaller the ion, the more important the activity effects are. So when are these things going to be important? They're going to be important when ionic strength is high, when we're talking about things that have big charges, or when we're talking about things that have a small hydrated radius. Then we're really going to need to pay attention to these corrections for activity effects. And we can do that by determining what these activity coefficients are. So how do we figure out what those activity coefficients are? Well, we can use an equation like the extended to Huckel equation to calculate them. This equation has been found to work well as an approximation, so it works pretty well as long as the the ionic strength is less than or equal to about 0.1 molar. So if we have really concentrated ionic solutions, then this is not a good way to determine what the value of the activity coefficient is. But we can measure the values of activity coefficients and put them into tables and look them up in those tables according to different ionic strengths. And so that's another way that we can go about finding activity coefficients. Okay, now that we know a little bit of something about activities, we're ready to start talking about the Gran plot titration method. So we're going to imagine that we're titrating a weak acid with the strong base sodium hydroxide. So they would react according to this equation here. So HA is our equation for the weak acid. So it has that one proton, H, that it could donate. This example is for a monoprotic acid, but this would apply perfectly well for a polyprotic acid as well. And so then we've got our strong base, which is our titrant. And because it's a strong base, it's going to react essentially 100% with our weak acid to make water when the H plus attaches itself to the OH minus, the hydroxide. And then we'll end up with sodium cations and then the conjugate base, A minus, of our acid. So in the traditional setup, we would put the sodium hydroxide into our burette, and then we would pipette a certain volume of acid into a flask. So this will be a known amount here. We'll call that VA, and we pipette that. And so it has some concentration that we may not know. That's typically the analytical chemistry goal, is to figure out that concentration. So I'm going to represent that by F subscript A, the A for acid. So F is going to be our symbol for what we call formal concentration. So the F for formal. And so formal concentration will be measured in units of molarity, but it could be millimolar. Really, any concentration unit is okay. But what's different about formal concentration is that basically it assumes that there's no dissociation or other kinds of reactions going on. And so, for example, if I have 0.1 molar sodium hydroxide, then that's kind of misleading, because that would say that I have 0.1 moles of these sodium hydroxide molecules floating around my solution. In fact, I probably have close to 0 moles of those sodium hydroxide molecules floating around in solution. Why? Because they essentially 100% break up to give me sodium cations and hydroxide anions. So even though my formal concentration is 0.1, my actual concentration would be closer to 0. And my actual concentration of sodium cations would be close to 0.1 molar, as well as my concentration of hydroxide, close to 0.1 molar. All right, so that's what we mean by formal concentration. Basically, it's just like molarity, but we're going to not consider the fact that, say, a weak acid might dissociate a little bit. So you'll have some HA that's undissociated, and then you would have some A minus that is dissociated. We're just going to lump all those together and think about that molarity. So similarly, our base is going to have some sort of concentration. We'll call that F sub B for the formal concentration of our base, our sodium hydroxide. Just a reminder here about molarity. So remember, when we take a volume and we multiply it by molarity, we get moles. And you can see that just from the formula. So if we take our volume, say 1 liter, and we multiply that by a molarity, let's see, 0.1 moles of something in every 1 liter, then you see that the liters cancel out, and we would be left with the actual moles, 0.1 moles. And so we can write that in a different way. If we take volume and we multiply it by formal concentration, that will also give us moles. So that's just a helpful thing to remember that we're going to be doing with as we work through this Gran plot. Okay, so let's think about what happens at the equivalence point. So we know at the equivalence point what's happened. We've added exactly enough base to neutralize all of our acid. So at the equivalence point, the moles of base added will be exactly equal to the moles of acid that we had present initially. So how can we set up an equation for this? Well, the moles of base added, that would be a certain number of volume, a certain amount of volume that it takes to get to the equivalence point. So we're going to call that VE. We're going to multiply that by the molarity, F sub B, right? And so that's where we're going to use this equation right here to determine our moles of base added. And that's got to be equal to the moles of HA. And so that will be the volume of acid that we carefully pipette over times the formal concentration of the acid. Now, like I said, in an analytical chemistry application, typically we don't know what that is, but the volume of acid is something we do know because we've pipetted that over. The volume of the base is something that's known. Why? Because it's a standard solution. So we have mixed it up or standardized it in some way so we know what that concentration is. And then the equivalence point volume in a titration, that's what we're always trying to measure. And so that might happen with a color change, or if we're using a pH meter, we're looking at some sort of behavior in the acid-base titration curve. Or in this Gran plot, that's what we're all about, figuring out a clever way to figure out what VE, the equivalence point volume, is. So if we're away from the equivalence point, then it's a good approximation that each mole of base converts 1 mole of our weak acid into 1 mole of its conjugate base, right? So just going back up to our reaction equation up here, each time we add 1 mole of base, it's going to convert 1 mole of acid to give us 1 mole of A-. Now, once we get really close to the equivalence point, because of equilibrium reactions and so forth, things are going to be a little bit wonky there, and so it won't be exactly true. So once we include all of those equilibrium reactions like autoprotolysis and all of those things, then this won't be exactly true. But if we're away from the equivalence point, then it is a good approximation. We can make that assumption. And so I say that because we're going to be using that assumption here. So what can we conclude? We can conclude that moles of our A- will equal the moles of sodium hydroxide that we added, right? Because each mole of sodium hydroxide that we add converts 1 mole of the acid into 1 mole of A-. So the moles of A- will equal to the moles of sodium hydroxide that we've added. Similarly, the moles of HA that are present in our solution at any point will be equal to the moles that we had initially. I'll use init as my abbreviation for initially, minus the moles of sodium hydroxide added. All right, so that's just making use of our good approximation here that as long as we're away from the endpoint, this should be true. And that will allow us to calculate the moles of HA and moles of A- at any point during this this titration, as long as we're ahead of the endpoint a little bit. So let's consider the acid dissociation constant. So we're going to imagine, I'm not going to write the water here showing that we would transfer an H plus to a water molecule. We're just going to imagine that that H plus pops off. Of course, in water, it's going to attach itself to 1 or more water molecules, form some sort of cluster. But we're going to imagine that this is the basic acid dissociation reaction. And it has an equilibrium constant expression that we call Ka, the acid dissociation constant, and it's products over reactants. And we're going to write those in terms of activities. So we're going to have the activity of H plus, and that's just the molarity of H plus times the activity coefficient for H plus. Then we're going to multiply that by the activity of A minus, and so that's just going to be the molarity of A minus times the activity coefficient for A minus. So it's products over reactants still, so our reactant is HA, so we need the molarity of HA times the activity coefficient for HA. All right, so we'll write the general expression this way. All right, we want to think about doing some substitution into this equation. So it turns out from our conclusions up here, we can actually calculate what this A minus concentration is and substitute that into this equation up here. All right, so what is A minus? So A minus is going to be the moles of sodium hydroxide added, right? Because we figured that out. Moles of A minus equals moles of sodium hydroxide added. So moles of sodium hydroxide added. And then molarity, right, is moles divided by liters. So we need to divide this by the total volume in our flask, right? What flask am I talking about? I'm talking about the one that we're titrating into right here, right? So remember, it had some initial volume, but then we've added some more to it. So we've added some base to it. And so writing that out in terms of like an equation, the moles of sodium hydroxide added, well, that's just going to be the volume of the base that we have added. We're going to call that VB times the formal concentration of our base. Remember, volume times molarity equals moles. So that's how we figure out how many moles we've added. Then we're going to divide that by the total volume in the flask. Well, that's the initial amount of acid that we pipetted over plus the additional base that we have added. So V sub A plus V sub B. That's our total volume. All right, so what about HA? We can also use this conclusion right here that tells us the moles of HA is equal to the moles of HA initially minus the moles of sodium hydroxide added, again divided by the total volume because it's moles divided by liters. So how many moles initially did we have of the acid? Well, the volume of the acid times its formal concentration. So like I said, we might not know what F sub A is, but it is something, right? It's a thing, so it is a concentration that exists. We're going to subtract from that the volume of base that we've added times the formal concentration of our base. Right? Volume times molarity equals moles. And then our total volume, same as before, VA plus VB. Okay, so now what we're going to do is we're going to substitute those into our Ka expression. So let me keep those on screen here. And we'll just write all that down here. So now our Ka is equal to H plus, that's still there, times gamma H plus, that's still there. And then instead of A minus, I'm going to write this stuff. I'm going to write VB times FB over VA plus VB. So that's what I write in place of this A minus right here. And then A minus still gets multiplied by its activity coefficient. Then we divide by HA. So instead of HA, I'm going to write all of this stuff. So VA times FA minus VB FB over VA plus VB. Just copying all that stuff down. And that's still going to multiply our activity coefficient for the HA. Okay, so now you will notice that I have a VA plus VB in the denominator upstairs in my numerator part, and I also have a similar VA plus VB downstairs. So it turns out I can just cancel those out. So that simplifies my expression a little bit. And now what I'm going to do is just rearrange things a little bit. So I'm going to multiply both sides by the denominator that's down here. And then I'm also going to divide by this. Yeah, so I'm going to just multiply both sides by the denominator down here. So this bit right here after I've canceled things out. So I'm still going to have my Ka on the left-hand side. Then I'm going to have VAFA minus VBFB times gamma HA. So that's going to equal all the stuff that was on the right-hand side. That's all still there, H plus, gamma H plus. Then we have VB times FB times gamma A minus. Okay, so now what I'm going to do to continue rearranging things a little bit, I'm going to divide both sides by this term right here, this FB gamma A minus. So I'm going to divide both sides by that. And so that's going to give me Ka. I'm just going to go ahead and move this gamma HA and put it next to my Ka here. Just kind of group those things together. And that gets divided by the gamma A minus from over here. Then I'm going to rewrite things a little bit so that I have this part, VAFA minus VBFB, and that got divided by this FB here. All right, and so that equals over here H plus on the right-hand side, gamma H plus times VB. Okay, so over here, I can rewrite this term right here. I can basically break it up into two fractions, subtracting two fractions from each other. So I have VA FA over FB minus VB FB over FB. Right, so just breaking it down into two fractions, right? You remember that our rules for adding and subtracting fractions, if they're over the same denominator, then I would just put them over one denominator and subtract the numerator bit. So I'm just undoing that. So you see now that our FB's over here on the right-hand term, they cancel out. What about this bit right here? Well, if we scroll back up, remember I told you that at the equivalence point, this was true, that the moles of base equaled the moles of acid that we had initially. So if we take this and we solve it for VE, you see that VE is equal to VA FA divided by FB. Aha, well that looks familiar. That's what this term is right here. VA FA divided by FB, that little bit right there, well that's just VE. So now clearing out some of the clutter, I have Ka gamma HA over gamma A minus times VE minus VB. And that equals H plus, gamma H plus times VB. All right, so let's remember our definition of pH because we're going to be using a pH meter to follow this titration. So our definition of pH was kind of approximate. You may have seen this approximate definition that pH is equal to the negative log of the H plus ion concentration. Right? So that would be pH. But it turns out that pH meters are actually not sensitive to the H plus concentration, but to its activity. So it is better to write that pH is equal to the negative log of the hydrogen ion activity. And so that is negative log of the hydrogen ion molarity, H plus in square brackets, times its activity coefficient, right? So we're taking the log of that. So if we undo the logarithm, take the anti-logarithm of both sides of this equation, well, take the negative sign first, then 10 to the negative pH is equal to getting rid of the negative sign and the logarithm out front, just this. So that's just undoing the logarithm. So I went from here to here just by taking an anti-log, taking 10 to a power anti-log there. All right, so you'll recognize that that's what this is right here on the right-hand side, left-hand side, sorry, right-hand side, yeah. So that's just 10 to the negative pH. We just figured that out. Okay, so I'm going to substitute that into this equation and go ahead and multiply through just a little bit more. And I'm going to take this term right here on the left-hand side and distribute it inside the parentheses. So I get Ka gamma HA gamma A minus times VE minus Ka gamma HA over gamma A minus VB. And that equals 10 to the negative pH times VB. So if we think about it, Ka is an equilibrium constant. It will have a constant value. These activity coefficients, in fact, aren't constant, but early on in the titration, when the ionic strength is pretty high, they're going to be approximately constant. And of course, the equivalence point volume is one fixed volume. That is a number. So all this stuff right here is just a constant. And so let's call that constant B. And then we're going to add to that all of this stuff right here, which again looks like another constant, right? K is constant, and I told you these activity coefficients are approximately constant, so let's call that constant. Just give it a label M. And it multiplies this thing. Now VB is a variable amount of base that we're adding, so it changes over the course of our titration. So that's going to be a variable. Let's give it a variable name called X. Now over here, the pH is changing as we do our titration, and so is the amount of base that we've added. So I could collect both of these into one variable name. We'll call that y. So I wrote it this way so that you can recognize that this equation up here has linear form. And this is the Gran plot equation. And it has linear form. So that's kind of cool. Let's think about what this plot would be. So I'm going to sketch out some axes here, an x-axis and a y-axis. So our x-axis is just going to be the volume of base. So this is what we're titrating, right? We start off with no amount titrated, and we keep adding base until we get to the equivalence point. Then this bit, our y variable, is going to be 10 to the negative pH times VB. So both axes are things that we can measure. We measure the volume of base from our burette reading, and up here we get pH from the pH meter, and again the volume of base from our burette reading. And so according to this equation, we should get a straight line. The straight line will have a slope, right? The slope is the m part, and the slope is going to be equal to negative Ka times gamma HA over gamma A minus. And then this point right here, that's our x-intercept, where the line intersects the x-axis, our x-intercept. That's going to be equal to, and you can see that up here, so the x-intercept, we want this side, the y side, to be equal to 0. So what would make this equal to 0? Well, this is a constant, so it can't be equal to 0. So what has to happen? VB has to equal VE. Aha! So our x-intercept is our equivalence point. So that is one of the big goals of doing a titration, right? So the first thing that we get by doing this Gran plot is we can plot it out. We figure out where the x-intercept is. We can do that mathematically if we know the equation for this straight line. That tells us what the equivalence point volume is, right? So the first thing we get, x-intercept, is equal to the equivalence point volume. The other piece of interesting information that we get is that the slope, from the slope, we can find the acid dissociation constant. So this Gran plot titration is also a way of measuring acid dissociation constants. So those are two useful things. So we're going to use this method to determine the equivalence point volume and determine the Ka of the acid that we're using. Now, in reality, when we're pretty far away from the equilibrium point, these data points do fall on a line. But as we get closer and closer to the equivalence point, we begin to see that it deviates from this line and it starts to curve away from the line. So that's because of two reasons. That's because these activity coefficients are in fact changing as the ionic strength changes, and also for the breakdown of that assumption that we made in this equation that 1 mole of base added produces 1 mole of A minus. Once we get close to the equivalence point, some of that A minus will be involved in a different equilibrium, and so we can't make that assumption. But what we can do is plot out our data and take the data from before the equivalence point that is linear and use that to find the equation of this line. We will get the intercept and the slope for the equation of that line, and then we can solve for the x-intercept, setting y equal to 0, and we can also use the slope value to find the Ka value, as long as we can use a table to look up these activity coefficients for our acid. So we would have to know the identity of our acid to do that. Anyway, so that's the Gran plot equation and how we will go about using the Gran plot method in this titration.